morning everybody. It's really nice to be here in Malaga. Coming from the UK, it's especially nice to see some sunshine, and I was organising a conference myself with David Hills, my colleague, last week, and it's especially nice to be at a conference where somebody else is organising, so thank you very much, Pablo. I'm going to say a little bit about what we've been doing in Oxford, and particularly I talked at Forney this summer about some work that we've done concerning uniform loading, but what I want to discuss today is really the case of non-uniform loading. Because the thing is that most laboratory experiments we do tend to be constant amplitude loading, for the fairly obvious reason that we want to sort of reduce the number of parameters in the experiment and so on. But if you take things like this, real structures, they don't experience constant amplitude loading. I mean, you can think of wave loading on an oil rig or gust loading or whatever on an aircraft wing, and you realise that they're very far from constant amplitude loading. In fact, I recall a few years ago talking to one of the engineers at Airbus responsible for fatigue lifing of wings, and he said something very interesting, which was effectively that we now have the technology and the control algorithms and so on, that if we wanted to, we could sense a gust coming, and we could change the geometry of the wing so as to dump lift from the wing and decrease the turbulence experienced by the aircraft and the passengers. He said the only thing is we haven't got the faintest idea whether this is a good thing or not as far as the fatigue life of the wing is concerned, because as we all know, and as I'll show in a minute, if you subject a structure to a single overload, paradoxically that tends to improve the crack propagation life. So we don't really know enough about the performance of structures under non-uniform loading, and there's no accepted consensus of how to predict crack propagation rates under these practical loadings. And certainly there are conferences that you go to, you only have to mention the C word, by which I mean closure, and you'll get a very spirited conversation going, in fact maybe an argument. So, where are we going on this? Well, I suppose the concept of stress intensity factors has proved extremely useful over the last 50 years or so, and most engineers in industry who are attempting to life real structures go straight to the concept of the stress intensity factor. But the stress intensity factor, of course, is based on an elastic analysis of the structure, and it doesn't in particular account for things like crack closure, whether roughness induced or plasticity induced or whatever. It doesn't account directly for plasticity. There are often three-dimensional effects which can be quite important, and as we've said, there can be non-uniform loading. So what I'm going to present today really goes back to some work some data which was collected by my student Paolo de Matos a few years ago, and it was really intended, it was on an aluminium alloy, and we were really looking for crack closure, and indeed we found quite a lot of crack closure. Now the focus of the Forney workshop and the one here is not so much what's happening, as it were, along the crack wake, but more what's happening in front of the crack. But in fact what I did at Forney was to reanalyse that data to examine the implications for what's happening ahead of the crack, and what I want to do today is to extend this for the case of non-uniform loading, and I think you'll find that there's some quite interesting features of non-uniform loading. So just to remind those of you who are at Forney, and to tell those of you who weren't what's going on, this is a fairly modest investigation looking at this aluminium alloy, compact tension specimens, and the idea really was to complement a lot of modelling work that Paolo had done. In fact, I think in many ways the experimental work turned out to be a bit more significant than the modelling work, but there you are, that's how things go. So what he did was measured the crack propagation rate, just optically, and measured crack closure both with a conventional strain gauge, looking at compliance, but also optically using digital image correlation. And it's those results that I want to think about today. And he used 3 different thicknesses of specimen, 3, 10 and 25 millimetres, really to look at whether closure was simply a surface phenomenon. And indeed, the conclusion is, and I guess it's fairly obvious, that it largely is. But I'm not particularly going to look at the different thicknesses today. The loading, most of it was constant amplitude, but there were a number of single overloads, and that's what I'm focusing on. And, as I say, we were looking for crack closure, so data was collected along the crack faces and not significantly ahead of the crack. But you can, as we will see, infer something about the crack tip behaviour from this crack weight information. So here's the bunch of experiments. Not particularly going to go into this in detail, but as you can see out of these experiments, we had 5 or so where there's an overload applied at some point during the crack life. Displacements, the most direct approach for investigating crack closure. What do we mean by crack closure? We mean that the displacements are such that the crack faces touch, and therefore the most direct way of looking for closure is simply to measure those displacements. Of course, those displacements are small, and so in the past people have used moire or laser speckle or something to try and give you some kind of enhanced resolution of displacements. But nowadays you can simply do image correlation, and if you've got a good lens on your camera, then you can get really quite close into the crack tip and get some good information. So this is what we did in the current work. And in a way of things, it was slightly well, it's an interesting kind of experiment. So we have a CT specimen and we have various gauges, and on one side you look at it with a conventional video camera, but on the other side we've got the most extraordinary experimental setup you could think of. It's a set of very expensive optics. It's a Questar long distance microscope, and coupled with not quite the most expensive optics you can buy, we have the cheapest camera that you can buy. So this is just a simple 640 by 480 pixel webcam, which was purchased, off the internet for, I don't know, £20 or £25 or something. And here is a set of optics which is worth several £1,000s. But in fact, of course, this is not such a stupid thing to do. Well, first of all, we already had this, and we were doing things on a shoestring. But actually, the sensors that they put on this are not terribly different from the sensors that they put on any camera. The cheap thing about a webcam is the lens. So what you do is you simply buy the webcam, throw the lens away, and put something good on the front, and you've got something that's very easy to interface with your computer. This is a typical. Now that's interesting. How do I? Yeah. Yeah, there we go. Okay. So this is a sort of typical video that we record. So you can see here we're very close into the crack tip. It's not entirely obvious where the crack tip is, but it's kind of somewhere here. And we've got about 0.5 millimetre that way by a bit less that way. We can get 30 30 frames per second, and we were cycling very slowly, so you get a lot of frames. Each pixel is about, well, you can see here it's 0.9 of a micron or something like that, so that the pixels are very close. Then extract the individual images and send them to an AVI file. And rather than trying to analyse the whole field displacement, what was simply done was to take a public domain piece of software from MATLAB and look at 5 different locations along the crack, and at each location you took pairs of points and worked out their relative location. And a little bit of data averaging was done around each position in order to get a bit more accuracy. And here I'm afraid I will have to come out of the presentation because for some reason it doesn't work within it. But here you can see what's happened. So the green is the original location of the points, and the red is where the software is tracking those points, and you can see it's doing a pretty good job of tracking the location, even though there's quite a rigid body displacement on the okay, so let's get back to the presentation. Okay, so that's what we're doing. This is a typical sort of output of that analysis for a pair of points. So what you can see in blue is the applied load, which, as you expect, is pretty sinusoidal. That's the loading. And the red is the displacement between a pair of points. And you can see up towards the top here, it's pretty sinusoidal, which is what you would expect for a crack that's open. And down the bottom here, it doesn't change. So we're varying the load, but the relative displacement doesn't change. So what this is telling you, of course, is that the crack is closed for this portion of the loading because at this particular location, because that displacement doesn't change significantly with load. Now, okay, that's fine, and you can go on and do an analysis of closure. But that wasn't what we want to do here. And when the Forney de Sopra workshop came along, we thought, well, what on earth can we present that's got relevance to crack tip stress fields as opposed to what's happening down behind the crack? Well, what you can do, of course, is to take the straightforward elastic solution for displacements, which gives the relative displacement across the crack as a function of position from the crack tip. And of course, if you know E here and we know the position, then we can fit a curve to this sort of form of expression and evaluate K, and we can see how good this fit is. So you'll see here that what we've simply done is taken logs of this, and if this expression is correct, we should have an r to the power 0.5 variation of displacement with position. And here you've got some typical expressions. So here we've got the distance from the crack tip in pixels, and here we've got relative displacement, and these are different loads. And what you can see is at this maximum load here, you get a pretty good linear fit, and the exponent is indeed about 0.5. So this looks as if the data is reasonably well represented by linear elastic fracture mechanics. Once you go down to here, and this is just above closure, you can see that maybe this is not quite so good, and indeed the exponent is not is quite some way from 0.5. And here you go. Here's a typical set of values for a whole range of loads. So initially the crack is more or less closed. Once we get above half the load, it starts to open, and you can see here how it opens, and you get a reasonable straight line fit for these higher loads. The other interesting thing is if you calculate the stress intensity factor using this expression and plot it against load, and what you find is you get this set of data here, and this is what you would expect if you from linear elastic fracture mechanics. So if you just work out what the relationship between K and load is for that geometry, and you plot that, and this is what you get from the experiment. So what you see is that for any particular load, there's a reduction in stress intensity factor, and that is what you, if you like, a residual negative stress intensity factor, which is caused by, if you like, by crack closure, or if you prefer to think of it otherwise, by the residual stress field around the crack. So essentially what we're saying is that until you've applied a load of this much, nothing happens, and then the crack opens, and then we get essentially a linear elastic response, and that's fine. We did think of then a more sophisticated model, and the one that we went to is one that was proposed by Sylvie Pommier and her co-workers, where you partition the displacement field into a conventional elastic term and a plastic term. And what Sylvie says is, well, you have your K1, which is the scaling factor for the elastic, and you have something called rho, which is the scaling factor for the plastic field, and essentially this is a sort of crack tip opening displacement or something of that sort. And what she says happens is that you have loading initially, and then unloading and reloading in the sort of K rho space. And that if you don't get very much variation in rho, then everything is pretty much elastic, and that corresponds to about the fatigue threshold. And once you start to get a cyclic crack tip displacement, then you're getting cyclic plasticity, and you're likely to get crack growth. So we can kind of do this, and we can fit this expression here to our crack data, and get this rho offset as well as K. Now, of course, if we had a pretty good fit to the elastic model, so what we should really expect is for this set of data that rho is very small, and indeed that's pretty much what we find. Indeed, if we just simply fit it, we get some values of rho which are negative, which is clearly not physically reasonable. But of course we should note that the crack tip position is not known with any great certainty, and maybe we might need to adjust that a little bit, and indeed you can adjust it a little bit, and you get this kind of loop. So here's the loading, and here's the unloading, so here's the K range, and we're getting a little bit of hysteresis in rho. So this might correspond to this kind of thing. And but in order to do this, we actually, to get sensible results here, we actually have to offset the crack dip quite a long way from where we think it is physically, just looking at the image. Of course, this may be correct, because we don't actually know where the crack tip is. Certainly we don't know how it varies through the thickness. We're only taking surface measurements. Right, let's go on to the non-uniform load, and the loading that we have is a very simple one. We apply constant amplitude loading, we put a single overload in, overload factor of 50% or so, and then we carry on loading at the same rate. So this is a set of data. Most of these are constant amplitude loading, so they just lie along this curve here, but we have a couple of specimens where an overload has been applied, and it's fairly obvious where it was applied. It was here. The crack propagation rate drops almost to a couple of orders of magnitude, certainly 1.5 orders of magnitude, and then it picks up again, but over quite a long distance. So this is longer than the plastic zone caused by the overload. If you measure, as it were, the crack opening load level, or the crack closure level if you like, here is, as it were, the steady state value, then immediately after the overload it falls, so the crack is almost fully open, and perhaps even if we could capture it, it would be fully open, and then the crack opening load increases till the crack doesn't open until it's loaded to about 80% of this load, and then it falls off again over this distance here, and so this bit here corresponds to this recovery, and by the time you get to here, we're back on the Paris curve. So that's what's happening. How does this pan out when we look at displacements? Okay, well here we are, here's the results before the overload, so you can see this is pretty much what we had before. Here's the theoretical line, this is our experimental line, a little bit of hysteresis, so we've got loading and unloading here, and a small kind of offset. When immediately after the overload, this is what you get. So again, this initially looks kind of pretty similar to this, but with a larger offset. But in fact, of course, what we realise is that now the stress intensity factors that we're getting out of the analysis are negative. And that doesn't make any physical sense at all. A positive stress intensity factor is fine, a negative one is fine as a sort of residual one, as a sort of way of thinking about closure. But total negative stress intensity factors don't seem to make any sense, because it would mean that the crack was interpenetrated. Of course, the crack isn't interpenetrated, and the reason it isn't is because there's now a significant crack tip opening. So what's happened is, when you overload the crack tip opens, and now we can take as it were, the crack faces coming together, but without touching, because we have this significant crack opening. So what you'll see here is this is our displacement data, and you can see these either almost zero slope of displacement with position, or negative slopes of displacement with position. And this is what happens if we do that more sophisticated model. So you see here that we have negative values of k for much of the cycle, just becoming slightly positive. Quite a bit of hysteresis in rho, this plasticity crack tip opening parameter. And look at the values of this. The crack tip opening now is about 12 or 13 pixels, whereas where we had this data it was, well, about 1 or 2 pixels. So we've got a huge amount of crack tip opening here. So there's some evidence here that we get a sort of K rho loop in the same kind of sense that Tommy is predicting. So just to sort of schematically let you know what's going on, this would be the sort of elastic crack profile. So as we load it up, we would just get square root variation, and as we unloaded, we would just go down the same path. If we've got an elastic plastic model, then what happens is we get a little bit of crack tip opening, and of course we get some hysteresis, so we get larger displacements on the way back than we had on the way up. But immediately after the overload, we've got this kind of situation where we've got a very big crack tip displacement, and we've got this rather peculiar kind of elastic variation of displacements going from this up to this. Now, this is where really the discussion starts, because I'm not sure what the implications of this are for the crack tip strain field, and indeed, of course, we didn't measure the crack tip strain field. We were only measuring things further back along the crack. Once we, the results I presented are for this point here, if you like. What happens when we get up to here? Well, you can see that this we've returned now to a rather more familiar pattern, So we've got this offset, we've got some positive stress intensity factors, we've still got some negative ones, and also you can see a hint here that we're tailing off into closure. So this is suggesting that even though we've got closure, there's still some kind of crack tip opening around as well. So the load versus K relationships that we get are very different in the three regions. Before the overload, under constant amplitude loading, we get something that's pretty understandable. It's linear elastic but with some offset. Immediately after the overload, the offset actually increases, and we get these negative stress intensity factors, but you know, that's corresponding to this region of low closure, whereas really we would expect offset to be correlated with closure, so you might have expected that the offset would decrease here, but that's not what we find. And then in the enhanced closure region, again, we've got a bigger offset than we've got here, which kind of seems sensible. So what are we going to do now? Well, as always, when you come to present something, when you write the paper, you sort of think that you're going to get further than you actually do, and of course we didn't quite get as far as we wanted to, because I've got a new research student, but he's got some outside interests, and that's him there. I'm very pleased to say that the crew did beat Cambridge, but as a consequence, he's not actually done as much on crack tip digital image correlation as I might have liked. But now that Cambridge are beaten, we can concentrate a bit more on that, and Sam is setting up some experiments actually this week. And what I would like to do is to just shift the camera along a little bit, so that we're looking a little bit ahead of the crack and a little bit behind, and we can try and correlate what's going on in terms of crack displacements with what's going on in terms of strain ahead of the crack. So just to conclude then, digital image correlation is very useful in terms of characterising surface displacement, although of course we should remember it's only surface, and we might get different deformation further into the crack, and this is where kind of techniques like tomography and digital volume correlation and so on come in. Constant amplitude loading, I think, in my mind, is relatively simple. But non-uniform loading is really very, very complex, and I think we need to do a lot more work in this area. I used to think that crack closure was a helpful concept. I'm sure, and others will be pleased to hear me say that I'm not sure now that it's quite so useful. I still think it exists, but I'm not sure that it's telling you the whole story. Until we understand near-tip deformation under non-uniform loading, we're not going to be able to analyse the kind of structures that I presented in the beginning. And just to point out that the whole lot was financed by the Portuguese government, which of course might be why they're in such difficulty at the moment. Right, thank you very much, everyone.